When you watch the ignition of a heavy lift rocket, you are witnessing the most powerful liquid fuel engine ever flown. This is the RD-170, a Soviet-designed machine that produces nearly 1.8 million pounds of thrust at liftoff. To maintain that fire, the engine must consume liquid oxygen and kerosene at an astonishing rate, ingesting literal tons of propellant every single second. Moving that much fluid instantly is the core mechanical hurdle. You cannot rely on the pressure inside the fuel tanks alone. You need a massive, highly specialized pump called a turbopump. To drive a pump of this scale, the RD-170's turbine requires 170 megawatts of power. That is roughly equivalent to the power output of 3 nuclear-powered icebreakers, all focused on spinning a single shaft. Designing a world-class rocket engine isn't just about managing an explosion. It is an exercise in extreme thermodynamic plumbing, specifically how to generate the immense power required to drive that pump. The reliable, baseline solution used in heavy-lift rockets like the Saturn V is the gas generator cycle. The plumbing is straightforward. A fraction of the propellant is siphoned off and ignited in a pre-burner to spin the turbine. The catch? This exhaust gas is simply dumped overboard, providing almost no thrust. This creates a constant tension for engineers. Every gallon of fuel used to spin the turbine is a gallon that isn't being used to lift the rocket, which limits the total payload capacity. The theoretical solution is the staged combustion cycle, where that exhaust gas is routed back into the main engine. But using kerosene fuel creates a physical roadblock. The combustion process produces thick carbon soot, or coking. Routing that soot-filled exhaust back into the engine would instantly clog the turbine blades, causing the entire assembly to melt and destroy itself. While American engineers focused on other architectures, Soviet designers like Valentin Glushko decided to tackle this kerosene soot problem directly. They developed a workaround that seemed counterintuitive, the oxidizerrich staged combustion cycle. Instead of a standard fuel-heavy fire, they flooded the pre-burner chamber with a massive excess of liquid oxygen. This flood acts as a coolant, keeping internal temperatures low enough to prevent the turbine machinery from melting. Because there is so much oxygen present, the kerosene burns completely. This prevents carbon soot, eliminating the coking problem entirely. Now that the exhaust is clean, it is injected into the main combustion chamber, creating a closed loop where zero fuel is wasted. This table shows the performance characteristics of the Energia booster. This closed loop achieves incredible efficiency, but it results in a staggering main chamber pressure of 3,556 psi. This design was such a metallurgical and thermodynamic success that after the Cold War, the U.S. aerospace industry spent 2 decades purchasing the dual-chamber RD-180 derivative for its own rockets. Today, the industry is moving past the RD-180, driven by the need for cheaper manufacturing and rapid rocket reusability. The shift is centered on a different propellant for next-generation engines, like the SpaceX Raptor and Blue Origin BE-4, methane, or liquefied natural gas. This graph compares the specific vacuum impulse of different fuels. As the methane curve shows, the propellant is highly viable, and it has one major mechanical advantage: it naturally burns incredibly clean. Moving from kerosene to methane changes the physical design limits of the engine. It allows engineers to use a plumbing configuration that was previously hindered by carbon buildup. This configuration is the pinnacle of modern liquid rocket engineering, the full-flow staged combustion cycle. Because methane is so clean-burning, engineers can use 2 pre-burners simultaneously, one running oxidizer-rich and the other running fuel-rich. This dual system drives the pumps even harder to create more pressure, while actually reducing the heat strain on each individual turbine. The performance leap is significant. This cycle allows engines like the Raptor to reach a thrust-to-weight ratio of roughly 200 to 1, surpassing the RD-180's ratio of 82 to 1. The history of the rocket engine is a series of solutions for managing pressure and heat. By moving from venting waste gases to recycling them through dual pre-burners, engineers have moved past the limits of legacy kerosene designs, providing the payload efficiency required for heavy lift missions to Mars.